Hola, amigos tensores. Hello, tensor friends. I ran into something here in my studies that I was unfamiliar with called the metric determinant. They just call it little g. It's equal to the determinant of the metric tensor. And I said, okay, I'm going to have to understand this. And like always, I have to start from the beginning because that's what I am. All right, so let's get rocking. Now, I've got this from the online PDF book that I have, Mathematics and General Relativity, a complete course. I'll leave a link in the description. Now, let me say, I don't get any monetary gain from recommending his books. I recommend his books because they're good, and I use them all the time. I use them for reference. I use them for learning new things. In this case, I'm learning new things. It's from his chapter called Tensor Densities. We won't get into that here because we don't need it at this moment. We're just trying to understand what is the metric determinant and who cares anyway. Okay, so I'm going to start out the same way he did. We want to convert our old Cartesian basis vectors E1 and E2 to a new set of basis vectors. Okay, so we're going to collect these guys as the row vector E1 and the row vector E2, and we collect them in a nice little matrix where we can take the determinant of that, which is 1, obviously. 1 times 1 minus 0. Okay? Now, let's do a little bit of geometric algebra. So the wedge product of vector A with vector B, as an example, gives the area of the parallelogram formed from those two vectors. Okay? Let's look at a drawing of that. All right, so here we have our x1 component, x2 component, the coordinates. Here is our E1 basis vector, E2 basis vector, right? So these guys form a parallelogram, right? So we can wedge E1, wedge E2, and this gives this the shaded area, which is called a bivector. E1 wedge E2 is called a bivector. And in this case, it's called the unit bivector because it has an area of 1, which is obvious because it's a square of side length of 1. So its area is 1. Okay? Now, we're going to choose a new basis vectors. And I'm going to use the same ones he did because they were nice. So the new E1 prime is equal to E1 plus E2, and E2 prime is going to equal to negative E1 plus 2 E2s, okay? Now, let's take the Jacobian of this so we can get our matrix, and we know how to do this. It's the partial of this with respect to E1 is just 1. The partial of this with respect to E2 is just 1. Partial of this with respect to E1 is minus 1. Partial of this with respect to E2 is 2. Okay, so now we have our Jacobian matrix. We can take the determinant of that and we get 3. 1 times 2 minus a minus 1 times 1 gives 3. Okay, so what is the area spanned by the new basis vectors? So once again, we're going to use the wedge product. All right, let's draw it first. All right, so here's our old basis E1, E2, and we formed these new basis vectors based upon those. So we went 1E1 and 1E2. So here's our new E1 prime. We went negative E1, 2 E2s, and this is our new E2 prime, okay? Now, we want to form a parallelogram between those two basis vectors. So the easiest way to do that for me is to add them together. So this orange vector you see here is E1 prime plus E2 prime. Then you go from the tip of E2 prime to the tip of the addition, the tip of E1 prime to the tip of the addition, and that forms your parallelogram. Now we're going to wedge E1 wedge E2 and find the area of this thing. All right. Here's the 2 rules you need. Remember the wedge product? So any vector wedged with itself is 0. And a vector A wedged with B is equal to minus B wedged with A. So they're anti-symmetric, just like the cross the product. Remember that? All right, so we're going to wedge E1 prime wedge E2 prime. So here's E1 prime, here's E2 prime. All right, now remember the rules. Here, this rule first. So E1 wedge E1 is 0. E2 wedge E2 is 0. So instead of getting 4 terms, we only got 2 non-zero terms, which is E1 wedge E2, which is 2, E1 wedge E2, and E2 wedge E1, which is negative E2 wedge E1. Now remember this, the property, right? So if I flip these two, it changes this sign, right? So when I flip A and B, it changes the sign. So I do that and I get 2 of these and now 1 of these. Now I can add them together and I get 3 of these. Well, we just saw above, this is the unit bivector, which is 1. So we got 3 times 1 is 3. So that's the area of this, which was also the determinant of the Jacobian, right? So you might remember from linear algebra, you can use the determinant of the Jacobian to find areas and volumes. This is the same thing. Now, we've got our background. So what is the metric tensor in the new basis? All right. Well, we know how to do this. We've done it many, many times. So G1 prime 1 is E1 prime dot E1 prime. Here's E1 prime dot E1 prime. You remember the rules. E1 dot E1 is 1. E1 dot E2 is 0. E2 dot E1 is 0. E2 dot E2 is 1. All right. So G1 prime 1 prime is 2. We use the same rules here. For G1 prime 2 prime, we get 1. And since we know the metric tensor is symmetric about the diagonal, we know that G2 prime 1 prime is equal to 1. These are almost always the same. As far as I know, they're always the same. I think that's one of the properties of Riemannian geometry, but I'm not positive. G2 prime 2 prime is equal to this. So this is E2 prime dot E2 prime, and we get 5. Now let's collect those in a matrix like this, and let's take the determinant, all right? So this is the determinant of the metric tensor Gij. So it's 2 times 5 minus 1, so we get 9. All right, so what's the correlation between this and all the other stuff? Well, here's the punchline. The determinant of the Jacobian is equal to the square root of the absolute value of the determinant of the metric tensor. J is the determinant of the Jacobian matrix. G is the determinant of the metric tensor, and they're equal via this square root. And you always see in the textbooks, they put an absolute value here because apparently this can become negative, which would be nasty to deal with. So that's 9 squared root of 9 is 3. So you can use the metric tensor to also determine these area of this parallelogram. And you say, well, why in the hell would you do that? That's 10 times harder than the other way. You're right, it is, but that's not its use. It's just you need, I shouldn't say we, I needed to understand where does this come from? Because they were writing J squared equals G, little g. And I was like, what? Okay, now I understand where this is from. Now what we're going to do with it. Okay, we can use the metric determinant to construct invariant tensor calculus operators such as divergence and Laplacian, and that's called the Gauss-Seidel formula, and it looks like this. All right, so we have the covariant derivative of this vector component is equal to 1 over the square root of the metric determinant times this partial derivative of this product. All right, so you can use this to calculate the divergence and Laplacians. That's what it's for. And the next time we're going to look at this and some examples of it. I'm not going to derive this in the next video because it is extremely complicated and it's just, it would take 2 hours to explain this. I'm going to point you to the beginning of this in Professor Fowler's excellent tensor calculator, the playlist. And if you really want to learn how to derive this, that's where it is. Okay, so I'll see you next time and we'll look at this thing some more. All right, thanks for watching.